tips and tricks, PID tuning examples and tips and tricks, and followed by a Q&A session. So firstly, a brief introduction to Epcos, who we are, and what kinds of services we provide. We are a company that for the past 18 years has been specializing in providing PID tuning, advanced process control, consultancy services for the process industries. We have been quite successful, I would say, in expanding our customer base to various parts of the world, and really actively engaging with new customers and really solving their specific problems. Our core skill lies in PID tuning, advanced process control. However, we are able to provide specialist services as and when required. The picture you see there is of the company about 3 years ago. It was a company event, and we are about 65 people now in Epcos. We've got offices around the world. The ones that you see in with the red background are Epcos' offices, and the ones with the white background are our partners. So really a global presence with a number of clients obviously spread around the globe as well. Now, what kinds of services do we provide? We are an independent, vendor-neutral provider of services. We do studies and audits. We provide PID tuning, base layer optimization. You see the various DCSs that we can work on, or we have experience working on. We also have quite a lot of experience in advanced process control in terms of implementation of advanced process control projects, maintenance, training. So really quite a wide range of skills and a wide range of experience in terms of the technology as well as the process experience, which spans refineries, chemical plants, fertilizers, and various other processes such as power. We have 2 PID tuning software products. One is called Inca PID Tuner, and the second one is Inca AptiTune. What we have for the 2 PID tuning products is effectively different types of applications. Inca PID Tuner is a single loop PID tuning software, and Inca AptiTune can tackle multiple interacting PID tuning problems. They are both fairly easy to use. They have a very simple workflow. They can connect to a DCS or PLC via an OPC connection. We can also do things like check the robustness of the PID calculation that we put together or calculate. We can also implement and simulate tuning before we implement it. And there's a library of DCS equations that we can choose from a drop-down menu. A logo, a slide full of logos of some of our customers. You will recognize some of these. And really, what this tells you is that we are quite a global company. Now, we'll start with multiple PID tuning examples. These are actual projects that we've done on PID tuning. Now, a prelude to sort of, before we go into the examples, is to really give you a flavor for what PID tuning is all about when it comes in the with respect to multivariable PID tuning. Fairly obvious to state, but PID tuning challenges are everywhere in your plant. It is quite important to identify and tackle these problems, otherwise they persist, and over time they can lead to other problems like safety issues such as wearing down of valves, etc. Really keep an open mind regarding the scope of PID tuning, whether it's single loop or multiple loops. When you start looking at a problem, you might find that there are interacting loops that are causing issues, which you probably did not envisage at the start of when you were looking at solving that problem. Also, if you have multiple interacting loops, it is actually not possible to tune them by using your standard rules of thumb or spreadsheets, etc. You really need some software to do that. And we believe we have Inca Aptitune, which is probably the only software that can deal with those sorts of problems. My first example is a gas plant in Saudi Arabia. This particular example is on a hot oil heater. The heater provides hot oil to the plant so that this is used as a heating medium on the deethanizers and other service. The type of problem here is to do with users of the hot oil, the fact that they are changing all the time in terms of the amount they use, as well as the set points that are set on the process side. Hence, the return temperature of the hot oil is always changing. So you get a lot of disturbances in the system. And what we did was we did a small test in this area where there was the loops were put in manual. And then after that, what we did was collected the data and entered it into our software and did the tuning. And you can see the before and after scenario here. A significant improvement in the exit temperature of the hot oil heater. My second example is of a propane compressor suction pressure. On this particular plant, the propane compressor was the heart of the plant, providing propane for chilling in various parts of the chill down section of the plant. And the client was never able to put this suction pressure in automatic. So it was always the compressor was always operating at a fixed speed, which is the red line here. And the result was that the suction pressure was changing all the time, which had a lot of impact, I would say detrimental impact on the temperature profile in the chill down section. So what we did here again was we made some steps, collected the data, and put the propane compressor in automatic. Clearly, a much improved suction pressure, and everybody was happy. Now, my next example is on an NGL recovery unit, and we'll go through this one. This was a multivariable problem. Again, just as an aside, if you could collect your thoughts and your questions and save them to the end of the session, and just type them through the chat box, and we'll get to your questions, as many questions as possible. And if there are still some outstanding questions left, then we will endeavor to email you with the answers. So coming back to this example, we have a feed gas header and an acid gas removal plant, and then we have the dehydration and NGL recovery units at the back end. So there's a feed flow controller at the front end of the plant and the pressure controller at the back end. And both these tend to interact quite significantly. So our challenge was to tune them correctly, and because we were implementing APC on this plant, it was quite important because both these MVs were quite important for in terms of the benefits that were likely to be generated from this plant. So we got together some step test data, and some of it was closed loop data and some of it with open loop steps. And then we put together a model, a 2x2 model, and this is using sort of the traditional APC modeling technology. And we end up with a highly interacting 2x2 system, as you would expect. And we use this model then as the basis for our tuning in our AptTune software. We started off with, this was an ABB DCS, so you can see here the initial tuning parameters and the final values. Clearly very different in terms of what the software was able to calculate. And we're quite comfortable with using, once you have done the design and the software itself and have taken into account things like how fast you would like your PV to reach the set point, what sort of disturbance rejection would you like, is there a limit on what is the maximum output movement. Once you've done that design in the software, then all you need to do is calculate and optimize the parameters, and you can enter these values directly with confidence, is what we found over the years of using this technology. Now, the before and after here isn't very exciting, but I think the main aspect here is the fact that we were able to keep these loops in automatic and make set point changes, and the PV would follow the set point, and really there was no instability being generated as a result of changing operating conditions, etc. And I'll come to robustness a little bit later on in the presentation. My final multivariable PID tuning example is on multi-flow tuning. I think we've all faced these problems. You could have multiple flows on a steam header, a fuel gas network, or hydrogen network. In this case, this was a sour gas header going into an acid gas removal plant, and you had 3 flow controllers effectively on the same pipe. And our objective was to tune these flow controllers and really keep them in automatic, so we could set a flow for each of these acid gas removal plants. Again, highly interactive, 3x3 system, as you would expect. And this is a screenshot showing you of a screenshot of the AptTune software, showing you sort of a configuration window where you can see all the different parameters. And you can see here the drop-down menu where, in this case, it was an ABB DCS, and the different parameters. This is a simulation window that shows you what happens in terms of the set point response when you make a set point change to each of the flow controllers, and the effect on the off-diagonal elements. The red is the set point change response, and the blue is actually the output response. I should just mention that. This picture here is showing you the robustness of the PID tuning. So what you see here is that to the left of this curve is the region where you are stable in terms of the PID tuning will be stable, and to the right of this curve you will hit instability. And what you have on these axes is a gain ratio and a dead time. So a combination of increasing the gain by a factor of 2 and increasing the dead time by 1 puts you around about here, which tells you you are still stable. So those models that you saw earlier, if those models changed by these factors, you would still be able to understand whether or not your tuning is stable. Extremely valuable because you would like your tuning to be stable and applicable for a wide range of operation, including things like, post-cleaning of exchanges, start of run, end of run conditions, etc. Again, this is available in the software as a standard sort of output. Now, here again, nothing spectacular in terms of before and after trends, but here the value was that we were able to put these loops in automatic and control them in automatic post-tuning. And obviously set those flows in our APC system based on the requirement for each frame. Now let's go through some single loop PID examples. The first one is a level. We all have encountered levels on our plants, and this is a level tuning example as well as it shows you the ease with which you can use the software to tune levels without having to collect data, so to speak. What we can do is sort of sit yourself in front of the DCS, put your level loop in manual, note down what is the initial value and the time, note down the value of the PV at the time you make your output change, and also the time you make that change in the output, and then note down the final value of the level. And you can enter these values directly in the software, and your next step is effectively you get a model that you can use directly to tune the PID loop. This here is before and after for this particular loop. The red is before and the blue is the after. And this is a disturbance rejection plot. And here is the before and after tuning in terms of parameters. So we started off with a gain of 2, and I think this is a reset of 0.2, and we ended up with a gain of 10 and a reset of 0.32. Again, significantly different tuning parameters as well as very good for stability. And I think we mustn't forget the impact of this tuning really on the process side, because really in this particular case the sulfur storage and degassing tank was able to reject disturbances more effectively. So you will have a similar story to tell for each of the loops you tune and the benefits that it generates for the process. This here is a demethanizer tuning example. It's effectively a temperature tuning example. What we had here was a temperature controller on a demethanizer, and the product from this goes on to a debutanizer where it gets separated into condensate. And tight temperature control of the demethanizer is essential so that we can have stable control of the debutanizer, and there isn't any carryover of light material into the debutanizer, which causes pressure problems. So really, again, a very, very important and practical problem that we are faced with quite often. What we have here is yet another method in terms of getting the data and building the model. We can cut and paste the data directly from an Excel sheet, for example. If you've made a few step changes, you can cut and paste the data, and then you can calculate the model directly in the software. Again, no need to get the data into the software through sort of an OPC server or sort of in batch form. And out comes a model. This model can also be specified in transfer function form with the time constant and the usual different mechanisms. So if you don't have data, you can also just, by looking at the DCS screen of the trend, you can, if you know the dead time, time constant and gain, you can just enter that information directly and use that as the starting point for your model. And here we have the red is the before tuning and the blue is the after. This is the set point change type of response. And what you see here is really a much improved set of tuning. To the left of this is the previous tuning, and here we did the test, put it in automatic, and then you see a much improved temperature control. You can see the final gain was 5 times bigger than the earlier one. So again, massive benefits on the process side just by doing a simple PID tuning exercise. Now we'll start off with the tips and tricks session. I aim to finish in about 15 minutes, and then we'll have some questions at the end. Okay, so equation is essential in any kind of seminar, so here goes. This is a standard PID equation, if there ever was one. There's the proportional term, the integral, and the derivative term. And sort of graphically, what this means is the proportional term kicks in and allows us to reject the error, so to speak, and drive us towards the set point. The integral term makes sure that we integrate out the error, so effectively remove the error and the speed at which we remove the error. And the derivative term puts a check on how quickly we make the change and acts on the rate of change of the error. Now, sometimes this K multiplies everything, sometimes it doesn't. So there's various forms of the equations, but I'm not going to go into that in detail. Now, when we are looking at tuning, we need to make sure we understand all aspects of the loop. There's the measurement. We need to think about whether the measurement is noisy. If there's analyzers, we need to worry about if they're frozen, spiky, or unreliable. Also, there might be calibration issues. So lots of things that you need to make sure are okay before you go ahead and say, okay, this is really a tuning problem, and let me go and tackle the tuning. Sometimes it could be other issues that are also causing you problems with poor performance of that PID loop. So think about the measurement. Valves, also very important. As you know, valves are far from perfect. You get stiction problems. You have valves that are oversized or undersized. Typically, they're nonlinear. The operating range is restricted. Sometimes positioners are missing. So again, think about the valve before you go headlong into doing PID tuning, because it could be just a sticky or a poor valve that is causing the problem. Filters, people sometimes think about filtering the measurement. This is related to the measurement, and sometimes they don't. But it is quite important for us to make sure that we are clear on the filtering and the filtering requirements of each sort of measurement by itself. And we can look at, visually inspect the filtering. We can put the controller in manual trend and measurement and see if it's reasonable. And then really we can say if it's quite spiky, then it's not enough filtering or there isn't any filtering. If it's heavily damped, it means perhaps there's too much filtering. And really there is a ideal type of filtering which you can inspect and check and sort of inspect and check and agree on. Now, the typical values for filtering in flows, pressures, levels, temperatures, these are just guidance numbers. There's nothing magic about this. You really have to make a judgment on the individual loop. So filtering is also extremely important. Now, there's the online tuning. So when you're going to tune a loop, most of the time people put the controller in automatic. They make a set point change and they observe the response and they see what to do next. So the first two pictures here show that the set point change was made, the PV response was slow, or there was an offset, so it tells us the loop was quite slow. The second one, the last one shows that really the response is very aggressive, so really also not acceptable. And then we have an acceptable response, which visually sort of we can all draw on a piece of paper and it looks something like this. So this is a good way of tuning simple loops, and quite often this is what we all tend to do. Derivative action is generally not used, but certainly in sort of the quick method or the online tuning method, but you can still use it if you have a lot of experience in doing that kind of thing. Now, tuning using model identification is the second way of doing things. What we need to do is to look at the model and then identify the dead time, the time constant, and the gain. And then we can use some tuning formulas, and there's lots of these formulas available, to come up with some tuning parameters. And these tuning parameters are calculated either by rules of thumb, people have their own spreadsheets, etc. And what you can do is, once you've calculated the tuning, you can either enter the values directly, or you can put the controller in manual, enter the values in the DCS, and then put it in automatic, make some set point changes, and evaluate the performance. There's also a similar mechanism for integrated type problems or levels or ramps. In this case, we look at different parameters, but we follow the same kind of procedure in terms of identifying the ramp or integrator model, and then we calculate the tuning using these rules of thumb or spreadsheet type of calculations. Now, robustness is an extremely important aspect of PID tuning, and sometimes people tune based on experience and estimation, and really what we want to do is to tune controllers robustly based on knowledge of that particular part of the process. You want to make sure that tuning is such that it reaches the set point quickly, it rejects disturbances, adjusts the valve when needed, and really can tolerate model errors. So really, if there is a change, like I mentioned earlier on, in the gain of the model or in the dead time, then we shouldn't end up with an unstable loop. We should have enough robustness so that if the process operating point changes, then the loop should be stable. For example, your plant is running at not 100% capacity, but perhaps 80% capacity or 70% capacity, then it should all be working. And the same also during startup conditions and shutdown conditions. So you want to span the full variations that you see in the plant, as well as the disturbances that you would typically see on your plant. And again, in terms of building that robustness into the PID loop, we can use the software that we have to calculate that robustness, as well as sort of design the robustness as well to some extent. Now, what are the things we need to look out for in terms of multi-loop tuning? How do we know if it's a multi-loop PID problem or if it's a single-loop PID problem, I suppose? And really, you can do that by putting the loops in manual and making some steps and seeing what those interactions are. You can use some APC modeling technology to come up with the various responses. Sometimes you have history, and operators will say, well, actually, I'm not being able to insert these loops in automatic for many months because they go unstable. So that's also an indication to you that this is a multi-loop PID problem, and it's not something that perhaps people have tried tuning one loop and it works for a short period of time and then it doesn't work. Heat integration is a big one. You always need to watch out for parts of the plant where there's heat integration, and these areas are good candidates for multi-loop tuning. I said already earlier that doing a multivariable model identification really helps you understand the process dynamics, and sometimes you'll be surprised at the interactions you find, things that you didn't actually think work that way. The other thing to watch out for is the dynamics of the process itself. It could be that you have slow times or long times to steady state, or you might have really fast times to steady state. And really you need to make sure you think about those when you're doing your model identification and tuning. Now, a typical PID tuning project, this is sort of like a checklist of things that you need to do. Make a list of the loops that you want to tune. Quite often that list is not exhaustive. Sometimes you need to start at the front of the plant and work your way through towards the back end of the plant. Make sure you have some mechanism of collecting real-time data. This could be data at a sort of 10, 15-second frequency or slower if you don't have that kind of ability on your IT systems. It's always good to define a test plan with your production people and agree that and start making steps based on the sizes that you have agreed. Extract the data and model the plant, and try and see if the control structures are appropriate to what you are designing. So sometimes you might want to reconsider changing a control structure like a temperature to reboiler, change it from tray 7 to tray 9 if you think that is a more sensitive tray, for example. But if the control structures are appropriate, then we optimize the tuning using a control technology and implement the optimized parameters on the DCS. And we can test the tuning by making some set point changes, document the changes, and really assess the performance after some time to make sure that nothing has changed and that the tuning is robust and works in sort of day and night conditions and also over different seasons and weathers and, hot and cold temperatures, etc. That sort of brings me to an end of the presentation. Thank you very much for your participation. There's a few little logistic things I'd like to go through. So if you would like a copy of this presentation, please email us at info@epcos.com and we will send you a presentation. We can also send you or we can provide you with an evaluation license of our Inca app, PID Tuner and Inca Aptitude software. Again, please send us your request via email and somebody will get back to you very quickly. Now, if there are any questions, I'll be happy to take them. and please submit them through the chat box, and we will get started. So I've got a question here. How do we tune cascade loops? To tune a cascade loop, we essentially tune the slave first and then the master. And really, this is sort of like a two-step process where you tune, you would collect the data for the slave loop, make set point changes in the valve output, get the model, tune the loop, and then put it in automatic, make steps in the set point, collect the data, and then also tune the master. You could actually do everything in one step by just making step changes in the slave loop and collecting the data. So that can also cut down your time in terms of how quickly you do that tuning exercise. There's a question here. If you can connect to data historians via OPC HDA directly, and the answer is yes, we can do that. And what is the equation for first order model? This is effectively the dead time, time constant, and gain, the standard equation that you have for a first order type of arrangement. Do you have any pattern recognition software that tends to detect stiction? No, we don't at the moment. I have just been told that for the OPC question, we have OPC DA, not OPC HDA. But again, if you have specific further questions, please just email us, and we'll be happy to solve your specific, answer your specific questions. There's a question on what is your experience of the value of improved PID tuning. And that's a very good question. We have done several projects where we go into the plant and look at a specific problem and or specific loops that need to be tuned based on the customer's request and focus on a part of the plant. And we have done several of these exercises, and the result really is that the client feels the benefits are significant enough for them to really do a full-blown PID tuning exercise. It's hard to put a number on in terms of dollars or benefits, but in the examples you saw in the demetanizer, temperature controller affecting product stream there on the debutanizer, which is worth a lot of money. So small improvements can result in very big financial, small improvements in PID tuning can result in very big financial benefits. I have nonlinear processes. How can Aptitude deal with that? We don't have a specific program as such that deals with nonlinear tuning as such. I suppose our mechanism of dealing with that is through robustness, where we design the PID tuning such that it's robust over a wide operating range. So we sort of deal with that that manner. Do you have experience on acetic acid reactors PID tuning? Yes, we do have some experience in chemical plants, but I don't have a specific answer to whether we have that particular. So please send us again just an email with the specifics, and then we'll be happy to help you. We have another question here. It says, what has been the most usual source of a loop issue you've come across? I think most unusual source of loop issues. I think there are all kinds of problems. Sometimes measurements have been swapped, and you sort of make a change. in a particular valve, and you think it should be affecting, and you don't see any change in the PV, and find out that somewhere along the lines, cables have been swapped, and so very, very strange problems like that, as well as sometimes errors in the PID blocks, or there's unusual amount of compression on the data, which causes problems sometimes. So those sorts of issues. And do you have tips on preparing a step test plan, number of steps, sequences? I suppose you would need to make sure your steps are big enough so they're outside of the noise band, and that's the first step. The second thing is to make sure that you are addressing the area of the plant completely, so you're doing a step test with all the loops in the correct mode, so that the data you get is all usable and in the right mode, so you can get the right interactions and models. Process inverse response. I suppose the question is, how do we look at process inverse responses in the context of PID tuning? We have the ability to use that model directly in our AptituneIn software. So if you have a non-minimum phase or inverse response, we can use that directly. So that is possible. Any other questions? I'm sorry if I didn't address some of your questions because it's a fast-moving thing, but I will make sure I go through all the items in the chat box, and if I have not addressed something, I'll be more than happy to email you, or please do email us as well and let us know if there's any further questions, or actually particular problems that you would like us to work on. Have you any tips for tuning split range outputs? I suppose the first tip is to really understand how it's working. Quite often these split range controllers have very complicated logics, and make sure that you put them in manual, make some steps, and understand at what point which output takes over. And you might end up with a scenario where you have different tuning constants based on the operating point, if your DCS allows you to do that. When tuning multiple loops with AptituneIn, can one of them be a ramp? Yes, indeed, it can be. There's no constraint on what those models or which loops can be included. It can be a mixture of ramps as well as steady state variables. Okay. Well, we've reached our 45 minutes. I very much appreciate your participation on behalf of Epcos, and thank you very much for joining us, and we will keep you posted on any future seminars that we might have. Thank you, and goodbye.